Hello friends, welcome to this video, and this video is a part of YouTube series Data Science and Machine Learning. Those who are interested in becoming a data scientist or who are already an expert and want to extend their knowledge or in data science, this YouTube series is for them. So in a last video we have seen how we could plot the two-dimensional data, two-dimensional two classes data. Okay, so and then we implemented the Python algorithm to find out the hyperplane. So in fact it was because the problem was two-dimensional, we found the hyperline equation, okay, automatically. Our algorithm just calculated or did the calculation or processing these data points given to it, and that is also called as when algorithm gets a data along with the labels to which it belongs to, then that data can be used for the training phase. And what the training phase does, it calculates the hyperplane, okay, and which is also called as a classifier. So that classifier gets trained, and then whenever the new point comes, a testing point comes, we also call them as a testing points. So when the testing points come, we put them and we solve the hyperline or hyperplane equation for that data point and decide which side it belongs to. So that's called as a testing phase. So now when we could do the things for the two-dimensional and we could find the two-dimensional hyperplane of for separating the two classes, why can't we do, or can we extend it for the 3D classifier? Yes, of course. So there will be a method. Just for example, in this graph you can see we have a three-dimensional data of two classes. The green circles are the one class type and red triangles are the another class types. And then we can get the centroid, this red one, okay, that's a centroid of this 3D. Now this centroid will have a x, y, z because it is in the 3 dimension, right? And here you can see that this is a blue or green one, okay, so that is a centroid for this red triangle classes. Sorry, you join this class, you join this line, and that will be the normal, vector. Now what is a normal vector? Normal vector for this plane, because you know this plane will be this normal line, and if we take a centroid as a midpoint of these 2 points, then it will be here. And at this point, if we draw the plane, perpendicular to this line, so actually this line is called as a normal for this plane, okay, normal vector of this plane. So when we have a normal vector, because a normal vector can be calculated, we have 2 points here, okay, so we can calculate the normal vector, and then we have a point on this plane, okay. So vector which is normal to this plane is known to us, and also the one point on this plane known to us, and using that we can calculate this plane equation. So now this plane equation will be nothing but the z is equal to ax plus by plus c, okay, in our 2D and 3D notations. Similar to the two-dimensional, when we tried to find out this line, hyperplane or hyperline, it was y is equal to mx plus c. So similarly, z is equal to ax plus by plus c will be the generalized equation for this plane, okay. Now as you can see, I think we changed when we started plotting the data in a 2 dimensions or the 3 dimensions, and then we started plotting the line. That time we changed the notations from x1 x2 to xy, okay. Okay, so if we go back to those same notation x1 and x2, then this z is equal to ax plus by plus c can be written as a x3. So z will become third dimension, so x3. So x3 is equal to a1 into x1 plus a2 into x2 plus c. Okay, which can also be written as a1 dot x1 plus a2 dot x2 plus a3 dot x3 plus k is equal to 0. Okay, so that's going to be a equation of this plane. Similarly, what was the line equation? A1 dot x1 plus a2 dot x2 plus k is equal to 0. Okay, so a1 dot x1 plus a2 dot x2 plus k is equal to 0. So two dimension x1 and x2. Okay, and this k is a constant, some value constant. Here x1, x2 and x3 and their respective coefficients a1, a2, a3 and plus k, right? So similarly, we can have a hyperplane equation as a1 dot x1 plus a2 dot a2 dot x2 plus a3 dot x3 plus so on up to an dot plus an dot xn plus k. So actually it should be plus here. Okay, so plus an is a one coefficient and xn. Okay, so I could not use a subscript there, but an into xn plus k is equal to 0. So same, I think, generalized equation in the series form, the summation I is equal to 1 to n ai into xi plus k is equal to 0, and this same equation can be written for the 3 dimension or 2 dimension or any dimensions. Now very interesting to see, I mean, hyperline we could draw like this. We could draw the 2D plane also in a 3D dimensions, but what about if the dimension increases from 3 to 4 or so on, or higher one? I mean, it's really not possible, or it is very vague to see how that hyperplane will look like. Somebody has drawn and then I just pasted it. So it's not worth explaining also, so I will not explain much about this hyperplane diagram. Let's go ahead. But yes, we got that we can, you know, 2-dimensional to 3-dimensional and 3-dimensional to n-dimensional, so we can solve the any dimension problem. We can solve the any dimension problem. That is what the aim of or objective of this slide. Okay, so next slide will give us the what are the algorithms when we have, because you know we have already come up with the in a last video, and then last video we implemented the same algorithm. So we came up with some our own algorithm of the machine learning which can separate the two classes. Okay, at least in the 2 dimensions we have already seen. We haven't seen 3 dimension, but we can also do the mathematical analysis, and we do the we come up with the algorithm to solve the 3-dimensional problem, or finding the 2-dimensional plane which will separate the 2 classes of the 3-dimension points we can have. Okay, so like this. So this can be extended to the 3D, and maybe we can I'm not sure, but it can increase to the other dimension also. So let us see. So what are the characteristics of the ML algorithm, right? So you know, both are, I mean, whatever we have done so far, what was the one, both are computational procedures, right? So whether it is a 2-dimensional, 3-dimensional we did not implement, but just theoretically we analyze. So these two things are computational procedures. I mean, just start with the given 2D or 3D point 2D or 3D points of the 2 classes, and then get the hyperline or the hyperplane from that. Now different methodology, actually here the different methodology, because there was there was a slope and y-intercept. Here there was no slope or intercept, but here the normal vector and all. So we can say the different methodology to the different dimensions. That means the same methodology adopted here cannot be extended as it is to the 3 dimension. right? And I'm saying this with the low confidence because even I so far I have not come across the literature, mathematical literature, where the 2D can be I mean, in this particular case, okay, in this particular case, I'm not talking about the all other algorithms. Okay, keep that in mind. I'm not talking in a generalized way. I'm just talking to the what the algorithm we implemented in a last video cannot be extended as it is to the 3D because their methodology is different. Here slope and intercept we used, here it wasn't like that. Okay, here it is a normal vector. So that is why I'm saying with the low confidence that it cannot be that particular algorithm which we implemented cannot be extended as it is or the very simplistically to the 3D and the multi-dimension or the higher dimensions. We cannot, right? But yes, if there is some mathematical algorithms or mathematical articles or literature which is explaining that, I think I'll welcome it to discuss on that, and I would like to go through that. Okay, now this both the approaches were the centroid based approach. Okay, now what is a centroid based approach? We know that we calculated the centroid of this and we calculate the centroid of this, or even in the three-dimensional centroid of this and centroid of this. Okay, so let's take an example of the two-dimensional centroid of this and centroid of this. So what was the objective out here was to just take a center of these 2 points. Okay, that was the objective of this. Here also the whatever the centroids we are getting, draw the plane at the center of that, right? But algorithm was not considering any scattering. That means if the scattering is higher here also higher, or here it is somewhat lower, then or asymmetrical scattering is there in across the 2 classes, then I think there could be an issue, and I think this diagram will show you that. Okay, so let's say there is a one data with this vicinity, this cluster. Okay, and this is a C1, so this will come as a centroid, and there is another data which is scattered like this, and it is a C2. Okay, if you take this centroid and this centroid and perpendicular line, you are going to get a perpendicular line over here, right? Approximately over here. Now ideally it should have been like this. Ideally it should have been like this, not touching the vicinity of this nor to this also. Okay, so here I think required was like this, the solution should have been like this, but actually with our algorithm this is we will be getting this, and that's why it is not able to separate this plane, or this line is not able to separate the 2 classes completely. Okay, so this is the kind of the drawback of the algorithm we implemented in a last video, right? So it is applicable if near ideal clusters, that means cluster is close to ideal, I mean, you know, very good clusters here, because you know, if the somebody see most of the points over here, but then little bit percentage of the points this side also, then the, you know, the cluster will get diverted, and it will become a longer one. And if the center, if the another circle, another centroid, another centroid, and its cluster is a very regular, the very ideal one, then this, because of the non-ideality, I think this problem will come, and that's why it is good for the if the both the clusters are near ideal clusters. Okay, for the both classes. Now there is no optimization out here. Whatever we get, we just keep on doing that, very mathematically, it is very procedurally it is, and there is no, you know, it doesn't go back and use a feedback in the algorithm, or while calculating the plane of hyperplane equation. It doesn't give a feedback. Okay, but if it is a optimization, we actually we decide maybe randomly or maybe systematically the final solution, and then we see the objective is satisfied by that solution or not. So if it is not, then we again we change the variables and try to bring it in the bring to the optimized final solution, right? So whatever the method we implemented, that has got these characteristics, and because of that I think there are some shortcomings and it will fail in the most of the cases, because real life data is not going to be ideal clusters, right? So SVM methods can overcome those shortcomings. It is going to definitely overcome. Okay, but what is SVM methods? I think we will have to wait for some time, and we are going to come soon on these SVM methods. For time being, we will ignore the explanation on the SVM methods. But yes, we understood that whatever the uh, machine learning approach we implemented or we explored, that is not enough to have a good solution in a classification, right? Okay, so now we have seen so far we have seen or we have discussed mostly on with the two classes data only. Okay, so hyperplane based classifier are mostly a binary class and only two classes. Okay, we have already seen. However, but yes, there could be a problems with the multiple classes also. For example, uh, there could be a or we have already seen there was a three class problem. Okay, the three species of iris flower, and that iris dataset is already available, and we have explored that a bit. So there are so many applications, or there are so many use cases where there will be the multiple classes, right? So yes, I think even though we have a binary class, okay, uh, need not to regret on that, because fortunately the binary classifier or bi-class classifier can easily be extended to the multi classes, to classify the multiple classes, to make it a multi-class classifier in most of the cases. Okay, so KNN actually is already an multi-class classifier, so we will not bother about it. But the classifiers which tries to find out the hyperplane to classify the two classes can also be extended to the multiple classes, right? And there are the two general methods to extend by class classifier to the multi-class classifiers. The first method is the one versus one, OVO. Okay, one versus one, and another is a one versus all, OVA, one versus all. Okay, so these are the two methods. If we use, we can easily extend the by class classification to the multi-class classifications. Okay, and then it will be interesting to see, I mean, if when it comes to these two types of methods, it will be interesting to see which methods, I mean, how to I mean, of course the name differs from one to another, from another, but how the computations or the number of classifiers will vary or not, that we are going to see in a, in a, in this video. So what will happen, I mean, this is our data 4 class. Okay, and now here you have a class 1, let's call it class 1. The exact opposite to that is a class 2. Okay, and it is written here also. Class 2 is a green circle, class 3 is a blue rectangles or squares, and class 4 is a horizontal directed, left side directed triangles. Okay, so this, so class 1, class 2, class 3, class 4. right? Now what will happen in a 1 versus 1, right? So in a 1 versus 1, what is going to happen? The class 1 and class 2, okay, so class 1, class 2, class 3, so class 1, class 2, class 3 and class 4. Now as name suggests, 1 versus 1, that means this let's consider for time being the this class. So this class will fight with this one, with this one and with this one, and while doing so it will consume a 3 classifiers. That means this versus this one classifier, this versus this one classifier, this versus this another classifier. Okay, so like that 3 classifiers will be used by this one. Now when I'm saying that, see, we have a data of the 4 classes, right? We have a data of 4 classes. Now let me just go back to the program and see, let me show you what I did. We already have a function of the 2 classes, okay, 2 classes data generation. So we did a 2 times that. So the first time I run that, the 2 classes generated, and second time I changed the centroids and centroids. Okay, you can also change the variance, you can also change the counts and all. Okay, so after changing you will get a 4 classes, right? And those 4 classes I plotted here with the red, green, blue and yellow. And then this is the triangle, circle, squares, and this is the this side triangle again. Okay, so this is how. Let me just run it again. Yeah, so this kind of the data we got, right? Class 1, class 2, class 3, class 4. Okay, so let me go back to this slide again. And now so we have this one class. So let us focus on the 1 versus 1. It's very simple. The this with this one classifier, this with this another classifier, this with this another classifier. When I say this with this means what? I have a data for all. I have a data for all, but one data either but it is a 4 class data. So while training or while generating the classifier for this versus this, I will use only these 2 class data. Okay, because as you know that the classifier we have is a by class only, can differentiate between the 2 classes only. So we will not take these data, we will take these data on as a one class, and these data as another class, because we know in a by class classifications we need a 2 label data only, 2 different labels data, 2 different classes data. Okay, so we will take this data only, the labels which are belongs to class 1 and the labels which belongs to class 4. Okay, 1 and 4, 1 and 2, 1 and 3, 1 versus 4, 1 versus 2, 1 versus 3. Okay, so if I see these and these, you know, this is going to be a classifier we are going to get, right? If we assume that we have used the same method which we implemented in the last video. Otherwise you can have SVM methods, you can have other methods also, there is no problem. This is a very general statement I'm talking. This is not specific to the any particular class of ML algorithms or classifier algorithms. But yes, those algorithms or the approaches, classification approaches, have a restriction that only 2 classes can be separated. Okay, so they are the bi-class classifiers. Okay, so now this versus this versus this, and this versus this, and then keep that in mind. Very, very, very importantly, very vital it is. Okay, when we say these versus these, that means we are using a data belongs to class 1 and data belongs to class 3 only, and we are making a this red one, this classifier. Okay, here also when we say that these versus these, we are using only this green label data, that means class 2 data, and class 1 data only we are using, and we are finding out these. And similarly for these also, this type of data and this type of data, that means the class 1 and class 4 data only will be used and to make. So in this particular case we can see that there are the 3 classifiers already made. Okay, when we started with this. Now if we start, is there any other combinations here? For example, with this we got these three combinations. So now we don't need, I mean, this versus this, this versus this means this versus this. Okay, both are the one combination is covered, either side it covered, it's okay, it's enough. Okay, we don't have to have 1 versus 2, 1 versus 2 and 2 versus 1. 1 versus 2 is nothing but the 2 versus 1 only, right? So we will not bother about that reverse one. So 1 versus 2, 1 versus 3, 1 versus 4 we got. 1 versus 2, 1 versus 3, 1 versus 4. Now 2 versus 1 we don't want, because it is already covered in the 1 versus 2. So 2 versus 3 and 2 versus 4. So 2 versus 3 and 2 versus 4. And now 3 versus 2 and 3 versus 1 are already covered, so we don't want. So 3 versus 4. Okay, so 3 versus 4 is remaining. So like that, 1 2 3 4 5 6 classifiers we have got. And again, keep the very important thing in mind, that when we say 2 versus 4, that means we have to use a data belongs to class 2 and data belongs to class 4 and train that classifier and call it 2 versus 4. Okay, there will be the another data, class 2 data and class 3 data, and train the data and call that classifier as a 2v3, 2 versus 3, so on and so forth. Okay, so once we have this, I think we will see how the testing will be done. We will see how testing will be done. But this one versus 1 means nothing but the all the combinations you are all the combinations where only 2 classes will be considered, and that will make a classifiers here, right? But there is another method. This is the another method, 1 versus all. So this is very simple. I mean, even simpler than the 1 versus 1. What it will do, this class versus all the 3 class, that means 1 versus 2 3 4. Now you can see, when 1 versus 2, that means class 1 and class 2 data only was used. Here when I saying 1 versus 2 3 4, that means the one class 1 data will be considered as a one side of the hyperplane, and class 2 and class 3 and class 4 combinedly, it will not make a difference whether it belongs to 2 or 3 or 4, but it will be considered as another class against the class 1. Okay, while making a 1 versus 2 3 4, right? So this is the biggest difference between these two methods. Here any classifier, any combination of classifier, let's say now 2 versus 1 3 4 it is going to be, 3 versus 1 2 4 it is going to be, not the 3. Okay, so yeah, so 3 versus 1 2 4 it is going to be, and 4 versus 1 2 3 it is going to be. So here again, if we take a 3 versus 1 2 4, 3 is this one, and all these remaining 3 classes will be taken as a second class, right? That means we have in this 1 versus all, you take any classifier, I mean any classifier, bidirectional classifier, you are going to extend it for the multi-class classification. That classifier, that bi-class classifier, will use all the data. Okay, whereas in this case it wasn't like that. If it is a 1 versus 4, that means only 1 and 4 class 4 only will be used the data for to train that particular classifier. Okay, here again this one, so we can call these also as a sub classifiers, also sub classifiers, right? So for all these sub classifiers will use all the data, but here it is not like that. Okay, so this is the difference. There is a second another difference we can see here. The number of classes are more. See, the 4 classes, both the problems has a 4 classes as a multi classes. Okay, but here 1 2 3 4 5 6, so 6 classes are required. So 6 times the training will be required, and here only 4 classifiers instead of 6, so only 4 classifiers are required. Okay, now let us see how we are going to use them. We use these sub classifiers to have a multi-class classifiers. Okay, so let's see, let's focus on the 1 versus 1. We have this yellow point, suppose. Okay, and we need to, and we know with when we do it with the 1 and anything, and naturally this belongs to 4. Okay, but anyway we are testing it, so we will see what our algorithm talks about, right? So this is the point, right? Now 1v2, 1 versus 2, so this is the 1 and this is the 2. So 1 versus 2, you will get a hyperplane like this, right? So you just make a matrix. You have a 4 classes, so class 1, class 2, class 3 and class 4, and on this side you write a classifier names. Okay, and you know how to give a classifier names. We have seen in the last slide how to give a classifiers, and that will change according to what method you are using, whether you are using a 1 versus 1 or 1 versus all. So if it is a 1 versus 1, you can see 1v2, that means 1 and this is the 2, 1 versus 2. So classifier will be normally approximately it will be like this, right? The hyperplane or the separating plane will be, or separating line will be like this. So it is going to be which side? This point will be going to this side. Okay, so now again, I mean, just focus on this, the 1 versus 1. Just consider this and this and this, and its separating line will be this, and since this is coming this side, its results will tell that it belongs to the class 1. So class 1 wins. Okay, class 2 losses, but we will not you know give a penalty for that. Okay, we will just make it neutral. Class 3 and class 4 were not in the ground. Okay, now 1 versus 3, if we take, so 1 and this is the 3. Okay, so 1 versus 3, this is the separating line will become, right? And again it is coming to this side only, and this side is a 1, and that's why the class 1 again wins. Now 1 to 4. Okay, 1 to 4, so this and this, the separating line will be this, and then separating line will be this, and then it is going to be this side, it is going to be this side, and that's why the fourth, 1 versus 4, fourth will get, so class 4 will have a 1. Okay, so class 4 will have a 1. Now say next combination, that this is the class 2 versus 3, 2 versus 3, so 2 versus 3, so this is going to be separating line, no, 2, this is a 2 and this is 3, so separating line is going to be this one. Okay, so which one is going to win? This, because this is a separating line, then this is on this point is on this side, that means the side where the class 2 is. Okay, and class 3 is opposite of this line, because this is going to be separating line for the 2 and 3, right? This is going to be a separating line. If you draw this, it is not drawn on this graph, but just with these mouse positions, with the mouse movement, you can imagine that this is going to be a separating plane, and if it is a separating plane, then the yellow point comes to the this side of, that means the class 2 side of the classifier, and not the class 3. Class 3 will be on this side, right? And that's why class 2 wins. So class 2 wins, so 1 right and other 3 will be nothing. Now 2 versus 4, so this is the 2 and versus 4, so the separating line will be like this. Okay, now it is going to 2 versus 4, so separating line will be like this, separating will be like this. So it is on the fourth class side. The yellow point is a fourth class, so 4 will win. Okay, now 3 versus 4, and I think separating line will be like this, separating will be like this. Okay, separating line will be like this, the hyperplane or hyperline will be like this, and here again 3 versus 4, I think the point will be on this side of the separating planes, so that means the class 4 is on this side, so class 4 wins. Okay, and now total them out, 1 1 2, class 2 has a 1 score, class 3 has a no score, class 4 has a 3 score, and 3 wins, and 3 is belongs to the class 4, so this point belongs to class 4. Okay, these yellow points or test point belongs to class 4. Now same thing we will see in a 1 versus all, and this is going to be a very simple as compared to the 1 versus 1. This one and then all the 3. Okay, so the first combination is a 1 versus 2 3 4. So we have already trained the classifier which has a one side class 1 and another side the combinations of all the data from the class 2, class 3 and class 4. Okay, so now since the point is here, and let's say if this is the centroid of the class 1, and what will be the centroid of these 3 classes, I think it will come somewhere here, right? And then if you put a divide into that, because the centroid for the all these combined classes, okay, 2 3 4 classes will be the here centroid will come here, and if you take a divide take a center point will come here and draw the perpendicular line, this is going to come here, and the yellow point will be on this side. That means 2 3 4 combinedly wins. Okay, and that's why that 1 mark will be distributed across 2 3 4, 0.33 0.33 0.33. Now take a 2 versus 1 3 4, so you have a 2 versus 1 3 4, so separating line will be somewhere here. Okay, and now here the class 2 will lose, so class 2 will lose and 1 3 4 will win, because it will be on the this yellow point is on the this side of the this line. Okay, this separating line, so 0.33 0.33 0.33. Next is 3 versus 1 2 3, so it is definitely it is coming to this side. Okay, so that means 1 2 and 4. Okay, here also 1 2 and 4 it was. Okay, yeah, here we already did. Yeah, so 1 2 4, here also 1 2 and 4 wins, so 0.33 0.33 0.33 and 3 losses, so 0. Okay, 4 this versus all these 3, so definitely it is close to this, so here will be the line and it will be on the this side of the 4 side of the class 4 side of this line, this point is, and that's why all the points, that means whole total score of the 1 will go to the this 4 only, it will not distribute it. Okay, because 0 0 0 and this is 1. Now if we add them we will get a 2, this we add 0.66 0.66 0.66, the class 4 is winning. So you can see you do it by this way or this way, whenever the point is somewhat closer to that cluster, I think you will definitely get a results same on the both methods. Okay, but that may not be the case, and that is why these two methods are the different, and that's and also the one method takes a more more data, another case take another method takes a more number of classes. Okay, so they are different, and though we have got a same results in both the cases, both the methods, they may differ in the some different type of the datas, or even the different number of the classes if they are trying to solve. Okay, so so we will see again, I mean earlier we have seen uh, four classes. Now let us look at the three class problems, then I think higher number of classes, and then we will have a generalized equation to find out the how many classifiers are required. So let's say we have a classes A comma B comma C, that means three classes there is going to be. So CF, now here the CF means classifiers or the sub classifiers we can say. So A versus B, if it is a 1 versus 1, A versus B, B versus C, and A versus C. Okay, total number of classifiers will be 3. If it is 1 versus all, then again classes are the same, A, B, C, that means 3 classes. So A versus BC, B versus AC, and C versus AB. So total number of classifiers is 3. Right, now we will take a 4, and we have just now seen that if A, B, C, D 4 classifiers, then A versus B, A versus C, A versus D, B versus C, B versus D, and C versus D. So total number of sub classifiers are 6 here. If it is a 1 versus 1 and 1 versus all, it will be simply the 4 classifiers: A versus BCD, B versus ACD, C versus ABD, and D versus ABC. So total number of 4 classes. So we have if we have a n number of classes, then total number of classifiers for the 1 versus 1 will be required is n into n minus 1 by 2. Okay, so for example, if n is equal to 3, so 3 into 3 minus 1, 2, 2 by 2, 1. So 3 into 1, so 3 number of classifiers. If it is a 4, okay, so it should come a 6. So 4 into, now what is this bracket term, 4 minus 1, 3, 3 by 2, 1.5, and 1.5 into n is 4. So 1.5 is nothing but the 3 by 2. So 4 into 3, 12, and 12 by 2, 6. So 6 classes. So similarly you can calculate if n is equal to 8, how much it is going to be. So how much it is going to be, n is 8, n minus 1, so 7 by 2, so 3.5, so 3.5, so we have a 8. Okay, so 3.5 we can write as 7 by 2. So 8 into 7, 56, and 56 divided by 2, that means 56 divided by 2 is 28. Okay, so 28, you know how exponentially it is increasing. Now for 4 it was 6, but 8, for 8 it is a 26 28 classifiers are required, right? So let's see for the 1 versus all, it will remain same. If it is n is equal to 3, it's going to be 3, 4, 4, 8, and 8. Okay, so in this case still I think we cannot generalize that. Okay, 1 versus 1 is a computationally extensive than the 1 versus all, because 1 versus all takes so many points, number of points more, and here it takes a less number of points. So training also depends on the how many points you give, because in each okay, we will see that those advanced things, but yeah, at this moment I think it is good to know that in a 1 versus 1 we need a n into n minus 1 by 2 subclassifiers, and 1 versus all we need for n classes we need a n classifiers. Okay, so that's all for this video. Thanks for watching.